Right, good evening. This is webinar, CAWASA webinar number 11 of 2024. Now, topic today is online process monitoring, applications and case studies. And our presenters today are from Xylem, and Justin King is the YSI production manager of process segment. He holds a Bachelor of Science degree in interdisciplinary business management and environmental science from the Miami University. He has worked at Xylem for 5 years as a product manager for all online process instrumentation, including YSI's IQ SensorNet product portfolio and the MJK flow and level product portfolio. We also have with us Ms. Adrienne Stenz, who is the application development engineer process segment. She holds a Bachelor of Science degree in Chemical and Biological Engineering from the University of Colorado, Boulder. She has worked at Xylem for 5 years. During her time at Xylem, she has worked with Flit Pumps, Sanitary Biological Treatment Solutions, and YSI Process Instrumentation. Currently, Adrienne is the application engineer for the YSI process segment covering wastewater and drinking water applications. So we'd like to welcome both of you and also to thank our regular participant on this event from Trinidad and Tobago, who kindly got our attention, Ms. Vishala Maharaj. So thank you all for joining us this afternoon, all our usual participants. And I now invite our guest presenters to take the floor.
All righty, thank you very much for the kind introductions, and thanks for allowing us the opportunity to talk a little bit about our online process instrumentation that we currently sell out of YSI, which stands for Yellow Springs Instruments. We are a brand from the larger company, Xylem Analytics, or just Xylem in general, who owns a lot of different water brands, including ones that you might know like Flight, Godwin, Sanitaire, Census. Anything in water, Xylem pretty much plays in it. So we're just a small piece and part to it, but very important for wastewater applications. And today, Adrienne and I will be talking a little bit about our online process instrumentation, which I'm the product manager for, and she's the applications engineer for, and and how we use this instrumentation in different wastewater treatment plant operations, as well as go over some of the high-level case studies and some of the real-world examples of where this instrumentation is used today throughout mostly the United States. But we do have a large presence worldwide with this instrumentation as well. So without further ado, I will jump into this presentation for the first 8 to 10 slides, and then Adrienne's going to take over for the large majority of the middle part of the presentation, and then I'll wrap us up at the end. So let's get into it here. So we like to start this presentation with just a typical overview of a municipal wastewater treatment plant. Now, as all of you probably know, wastewater treatment plants, none of them are set up exactly alike, and they all have different processes, but generally all wastewater treatment plants are going to follow some sort of pre-treatment, primary treatment, secondary treatment, and sometimes tertiary treatment, as well as sludge handling processes. So there's plenty of different control strategies and different ways to set up each one of these different treatment stages within a wastewater treatment plant. But the goal remains the same, right? The goal of a municipal wastewater treatment plant is to use physical, chemical, and biological processes to remove pollution and convert that wastewater into some sort of clean water, whether that is clean water that's going to be sent back into a lake, river, stream, or ocean, or clean water that's going to be sent to a reuse application. So I like to just start this presentation with an overview and just let you know kind of where we're going with this presentation. We're going to start at the pre-treatment stage and work our way all the way through these different buckets of treatment throughout a typical plant. And along the way, we're going to talk about online sensors and how they're used and where they're used to make the treatment process more efficient, and how they're used to help clean the wastewater along the way. All right, so online process instrumentation. For some of you, you may be very aware of online process instrumentation. For others, this might be your first time hearing about it. So I like to cover kind of what online process sensors and instrumentation is and what we can do with it. So for at least our product portfolio or our suite, we can measure a wide variety of parameters. This includes pH and ORP, total suspended solids, dissolved oxygen, ammonium and nitrates, even sludge level using an ultrasonic sludge level sensor. And then we have a suite of UV sensors, which is this big one in the middle here, which can measure a host of different parameters, including nitrate, nitrite, TSS, and a lot of different carbon parameters, including COD, BOD, TOC, and then of course, since it is a UV measurement, we can do the traditional UVT 254 measurements. And then we can also measure, we also do have some wet chemistry analyzers, which I'm starting to see more and more at wastewater treatment plants. And our host of wastewater treatment analyzers can measure orthophosphate, ammonium, and we have a chlorine analyzer as well. And so as we move throughout the presentation today, we'll talk about where it's best to use these sorts of sensors to gather continuous data on the process and why you would want to use these sensors in the certain applications. But first, let's talk about why would we want to use online instrumentation in the first place? A lot of plants, a lot of smaller plants in particular, don't use online instrumentation and never have. They typically rely on grab samples and lab samples to ensure that the process is working effectively and properly. But what can online process instrumentation bring to a plant in today's day and age of technology? Well, first, it can make the process more efficient. So instrumentation can tell customers how effectively they're doing or removing pollutants. So like for BOD, ammonium, and nitrate, we can measure all that with sensors and determine, and we can get data 24/7 to determine how well the process is accomplishing what it was designed to do. As opposed to using, just spot measurements through portable instrumentation or lab measurements via grab samples. Next, and what I think is the most important part of online process instrumentation is that it can be used to control the process. So this constant 24/7 data flow can be used to control different processes. And what that outcome is it makes the process more efficient. And by doing that, we can reduce energy cost and we can reduce chemical dosing cost and tons of other costs throughout the plant that you wouldn't typically maybe associate with with instrumentation in general. So for example, if we use dissolved oxygen sensors to control the aeration basins and the blowers, and we can create the most efficient aeration process possible, possibly saving thousands of dollars throughout a year in energy cost for running those blowers. Similarly, we can also save a lot of money in chemical dosing with something like an orthophosphate analyzer, where we're chemically dosing alum or some other chemical to flocculate phosphates in the water. We can use the orthophosphate analyzer to make that process as effective and efficient as possible, and that often saves the end user a lot of money in chemical costs. Also, instrumentation like this can help alleviate maintenance costs. This saves operators a lot of time from collecting grab samples and doing spot measurements. We all know that operators are some of the busiest and hardworking people in the industry and always have been. So removing some of their time on the basin with online instrumentation allows them to tend to more critical or other issues that are going on with the plant. So online instrumentation can almost be seen as like a second operator or an additional operator on the team, as it's collecting a lot of the vital data and process information that's used to make informed decisions on how to control and adjust the process accordingly. And then finally, online instrumentation is used for compliance monitoring and process assurance. So as all wastewater treatment plants are regulated by local permit requirements, state and federal permit requirements, online process instrumentation can give you 24/7 data on the effluent, ensuring that your effluent water quality is within regulation of whatever the permit states, as well as on the other end of the plant, we can monitor to make sure that there is no illegal loading or slugs coming from process industries. I don't think we talk about it in this presentation, but we've had our instrumentation used in the past to kind of catch different industry polluters from polluting wastewater treatment plants by utilizing our instrumentation farther upstream in the collection system. And it helps mitigate problems once those slugs or chemical loads get into the plant. So those are the four main reasons that we use online instrumentation today, and the four main ways that operators and plants can benefit from online instrumentation. So like I was talking about a few slides ago, these are the different steps of the process that we're going to walk through today. I'll be talking about the inlet, monitoring, and then Adrienne will pick up right around primary settling and take us through activated sludge. And then I will wrap us up with the effluent and talk a little bit about some of the sludge handling applications that our instrumentation fits well in. So let's start with inlet and pretreatment here. So the inlet stage is where the untreated wastewater comes in from the collection system and is received to the plant. In this stage, it's typically physical separation steps that remove large debris and heavy solids from the water. And we typically achieve this by using screens and grit chambers. So what kind of online instrumentation is most effective in the very beginning steps of a wastewater treatment plant? Well, that is typically pH and TDS, as you can see here. So, but we also can measure TSS and BOD as well as ammonia. So monitoring the pH, TDS, and TSS can provide early signs and of upset conditions. So if we have cases where there could be incoming chemical slugs that could wipe out the bugs in the activated or primary treatment stages, we can mitigate that and divert that water flow if we have online instrumentation constantly monitoring the inlet of the plant. And then for process control, we can, this kind of sets the baseline for process control. We can utilize these measurements. We can utilize pH, TDS, TSS, and BOD to determine how well our processes are working downstream. So as water is working its way through a wastewater treatment plant, ideally through each stage, it's getting cleaner and cleaner to some degree in some way, shape, or form. And by knowing where the wastewater is starting at, as far as monitoring the BOD and ammonia and the influent, we can tell how effective the process is during later stages in the plant. So those are the main reasons that we want to measure in the very beginning of a plant. And so next I want to show you an application example. So in this application, we've got a TSS and conductivity sensor installed in the inlet of a plant. These sensors are actually mounted into a side stream application, which is plumbed into a 2-inch PVC pipe and utilizes insertion mounting. So you can see the two sensors there, and then those sensors actually connect into our YSI 2020 controller, which will go back to a SCADA or PLC, or it can be used just as a local display as well. And so the TSS sensor in this application is used to provide an early warning of any slug loading. So in this particular case, upstream, we had a meat processor plant, and a lot of meat processing waste was received at this plant. And that excessive waste caused problems later on in the plant. So they were able to monitor the inlet of the plant to ensure that they weren't receiving excessive loads that could affect the plant's processes later on. And then they also they used a conductivity sensor to measure TDS, which helped them identify causes of excursions of chloride discharge limit. The TDS can be used for a compliance measurement, especially in where there's industries that dump high levels of dissolved metals, because high levels of dissolved metals can definitely disrupt wastewater treatment processes. So they were utilizing this small system, which ended up all in all, with today's 2024 pricing, ended up being around $10,000 to basically monitor for early upset conditions and create. And what they did based off this data is they created mitigation plans for when they did see upset conditions, which is a really cool application, and it helped save them a lot of hassle and trouble because they were able to keep their bugs in the activation basin happy because they weren't being loaded down with high levels of dissolved metals and high levels of meat processing waste. All right, Adrienne, I think you are up for this section.
Awesome. All right. So the next step in the wastewater treatment process is primary treatment. This step is responsible for removing as much organic or inorganic solids from the water as possible. This is usually done using large primary settling tanks, known as primary clarifiers or fine screens. So the main purpose of this step is to produce a liquid that is suitable for the next step, secondary treatment. Parameters that are typically measured here in primary treatment include TSS, sludge level, ammonia, and BOD. Monitoring these parameters can improve your process as the next step, secondary treatment, is optimized by the correct ratios of these nutrients in the water. So the right ratios of BOD to ammonia, BOD to nitrate. So by monitoring these parameters in your primary clarifiers, you can ensure you are removing the correct amount of nutrients in this stage to support the next step in the process. The next step in the process is secondary treatment. This step is the second step, let's see, this is usually referred to as activated sludge treatment, and typical secondary treatment basins include aeration tanks, trickling filters, oxidation ditches, or SBRs, sequencing batch reactors. In this stage, pollutants in the water are removed through the use of microbial bacteria. Typically, oxygen is added to the water in this stage through big surface mixers or through blower aeration systems. Adding oxygen to the water here promotes the growth and reproduction of certain bacteria that perform certain processes that rid the water of organic material and of ammonia. Water quality parameters are very important to monitor in this stage because achieving and maintaining the best environment for these bacteria is difficult and requires a lot of monitoring to control correctly. So the important parameters here are DO, ammonia, TSS, nitrate, ORP, and pH. Each of these parameters can be used to monitor and control this stage of the process, and I'll talk a little bit about each in these next few slides. The highest cost typically of operating a wastewater plant is the cost of running blowers for aeration in your aeration basins. And if blower speeds are not controlled and instead set to some specified airflow output, then chances are a lot of money and energy is being wasted on running those blowers. So the most common control scheme used in secondary treatment is dissolved oxygen aeration control. In this control scheme, blower speed is adjusted on a VFD to maintain a DO concentration set point in your aeration basin. So we're using online DO sensors to control our blowers and maintain a DO set point. The most common set point is 2 milligrams per liter DO. So why is that the set point? Well, we want the most amount of nitrification for the least amount of DO to be efficient. Nitrification is a biological process where ammonia is converted into nitrate. Below 2 milligrams per liter dissolved oxygen, the reaction rate for nitrification increases significantly with the addition of more oxygen. And above 2 milligrams per liter DO, when DO increases, the reaction rate for nitrification only slightly increases, meaning that any extra DO above 2 milligrams per liter is essentially wasted energy. So that's kind of where the 2 milligram per liter set point came from. Controlling via these nitrification reaction rate also ensures BOD removal, or the removal of organic material in the water, because BOD removal occurs at any oxygen level above 0.5 milligrams per liter. So this is probably the most common control scheme used within wastewater plants. This is an example layout of dissolved oxygen aeration control. In this example, DO sensors are distributed to be representative of the aeration zone that they control. So one DO sensor is placed over each aeration grid. DO can be maintained at 2 milligrams per liter set point at each zone, or it can be cascaded with lower DO set points per pass, which is typical when you have these long passes that are flowing through. So for example, DO might be maintained at 2 milligrams per liter at the first pass, then decreases to 1.5 milligrams per liter in pass 2, 1 milligram per liter in pass 3, etc. This cascading DO control theory works because the concentration of those pollutants in the water will decrease as they pass through the reactor, and thus you need less oxygen at the back half of the tank to treat the lower pollutant load at that point. Another control scheme that is used to control aeration in secondary treatment is ammonia-based aeration control. In ammonia-based aeration control, also known as ABAC, an ammonium concentration set point is used to control the blowers for aeration. Oftentimes, ammonia and DO sensors are used together to control the nitrification in these basins. So we just talked about traditional DO control, which suggests maintaining DO of around 2 milligrams per liter in your basins to facilitate the removal of ammonia and organic material, BOD. However, in plug flow applications where the concentration of nutrients varies along the length of the reactor, oftentimes nitrification is complete prior to the end of your train of treatment, and thus maintaining DO at 2 milligrams per liter leads to excess aeration and wasted energy. So controlling via ammonium as opposed to DO can lead to an additional 10 to 20% energy savings when compared to just the traditional 2 milligram per liter DO control. This can have other benefits as it ensures that you are removing all of the ammonia from the water, and thus you can verify you are meeting your permit limits for that nutrient. And a lower DO concentration in your basins can have other benefits for your process as well. Can you go to the next slide? So this is an example layout which is using both ammonia and DO sensors to control aeration basins. DO sensors are placed over each aeration grid, and the DO levels are cascading, starting at 2 milligrams per liter in the first pass, and then decreasing by a set point of 0.5 milligrams per liter per pass. Ammonia sensors are also included in each pass to monitor the ammonia levels. If the ammonia levels rise above a certain set point, then aeration is increased to ensure complete nitrification and removal of ammonia by the end of the aeration tanks. This is an ammonia-based aeration control application example. In this case, DO sensors, ammonia sensors, and total suspended solid sensors were used to fine-tune the aeration in their aeration basins. They use the DO sensors to ensure that DO levels never raise above 2 milligrams per liter. And then they use the ammonia sensors to further trim back their aeration. The total suspended solid sensors are used to monitor the MLSS, or mixed liquor suspended solids, which is essentially the amount of microorganisms within the aeration basin that are performing the removal of ammonia. And then this is a case study done at Brockton Advanced Water Reclamation Facility in Massachusetts. They did a case study with our ammonia sensors during a major upgrade that involved installing all new aeration equipment and instrumentation in an effort to improve their nitrogen removal and improve their aeration efficiency. The first step of this big study that they did was a head-to-head trial with 3 manufacturers' ion selective electrode ammonium sensors to determine which would work best for them, since having a reliable ammonium sensor is important for ammonia-based aeration control. The trial between the 3 manufacturers' ammonia sensors was done over 18 months, and they eventually chose YSI based on our sensor's accuracy, the lifetime of our sensor's electrodes, and its ease of maintenance. The second phase involved installing all of the new aeration equipment and instrumentation over the course of a year. And then the final phase was a 7-month period that was designed to optimize their ammonia-based aeration control. In these 7 months, they tested the ammonia sensor at different places within the aeration basin to determine the optimal placement for the ammonia sensor for ammonia-based aeration control. This was the sensor configuration of each treatment train at Brockton. DO sensors were placed in the aerobic zones to monitor the dissolved oxygen concentration, and optical nitrate sensors were placed in anoxic zones to measure nitrate. The question, of course, that they were looking at was where to place their ammonium sensor to ensure accurate ammonia-based aeration control. So at first, they tested an ammonia sensor in the influent and effluent of each treatment train. In theory, this is attractive because you can monitor the influent ammonia concentrations coming into the basins, and then the effluent ammonium concentrations coming out to ensure that you are removing ammonia from the water and meeting your discharge limits. However, this did not prove to be very effective for them because they found that the effluent ammonia sensor consistently read 0, which does not give much information. Although you can ensure that your ammonia level is near 0 when leaving your basins, it still doesn't tell you anything about how far upstream nitrification may be complete, and therefore is still resulting in excess aeration and wasted energy most likely. So they decided to move the effluent ammonium sensor upstream, right in the middle of the first aerobic zone, specifically where the ammonium concentration fluctuated daily between 1 to 5 milligram per liter. This proved to be very effective. The sensor worked remarkably well at this location and provided great data to best optimize their aeration process. They learned that if they can control with a set point at this location of 1.5 milligrams per liter ammonium, then they could ensure that they were achieving a near 0 ammonium at the effluent of their treatment train. So if ammonia levels were above the 1.5 milligrams per liter set point, the fourth zone, the anoxic zone, would be aerated to provide additional treatment. And if the ammonia levels were below the 1.5 milligram per liter level, then the fourth zone, the anoxic zone, was non-aerated since it was not needed. So by placing their ammonium sensor here in this location, they found this was the best environment for that sensor, and they were able to trim down their energy costs on blowers by about 20%. Another part of secondary treatment is phosphorus removal. Phosphorus can be removed either biologically or chemically from wastewater. Chemical phosphorus removal requires dosing a metal salt such as alum or ferric, which binds to soluble and particulate phosphorus in the water, creating a solid flock, which is then settled out in the next step in secondary clarifiers. A feedback or feed-forward control system using an orthophosphate analyzer is often used to control chemical dosing for phosphorus removal, reducing excess chemical use and saving money for a facility. So many facilities see an ROI of 1 to 2 years when adding an orthophosphate analyzer to automate this chemical removal process. So this is what an automated chemical removal system looks like. Some systems may have different or multiple dosing points, but we will look at this particular application called simultaneous precipitation. Simultaneous precipitation begins by dosing your alum or ferric at the end of your aeration basins, which with enough mixing will bind to as much phosphorus as possible. The water then moves on to a secondary clarifier in which those solids are settled out, taking phosphorus with it. The clean water then moves on to effluent treatment, which we can place an orthophosphate analyzer in to measure orthophosphate and provide a feedback signal back to our pump, which is dosing chemicals in our aeration basin. This is a case study done at a facility in Wisconsin, which saw significant savings on the cost of chemicals for chemical phosphorus removal by implementing an orthophosphate analyzer. Prior to the analyzer, operators were manually dosing ferric chlorides based off of phosphate grab samples, which they took twice per day. Operators would dose large amounts of chemicals to be conservative and to ensure that their effluent phosphorus limit of 1 milligram per liter would be met. So before installing the analyzer, they would spend almost $100K per year on ferric chloride. The plant implemented an orthophosphate analyzer to automatically control dosing of the chemical. And after the first year with the analyzer, they saved about $23,000 on chemicals, which was about the cost of the analyzer. So they saw an ROI within 1 year. And since implementing this analyzer, they have spent about $60 to $75K per year on ferric chloride. So we've talked a bit about aeration basins, which oxygen is added to the water through aeration systems to remove BOD and ammonia from the water. Some secondary treatment processes are modified from that typical just aerobic environment to help improve the biological removal of nitrogen and phosphorus from the water. This is done by creating different biological environments, anaerobic, anoxic, or aerobic, which grow select bacteria in each environment, which play a part in removing nitrogen or phosphorus from water. So these BNR, biological nutrient removal systems, monitoring for ammonia, ORP, nitrate, phosphate, and TSS are the common parameters that are measured for process control. There are three main biological environments used in biological nutrient removal processes to reduce nutrients, nitrogen, and phosphorus in wastewater. Aerobic zones refer to zones with both free and bound oxygen present, indicating zones that are aerated with diffuser blowers or with surface mixers. Anoxic conditions refer to an environment where bound oxygen is present, but not free oxygen. So bound oxygen is present within molecules like nitrate, which is NO3. Aeration is not added to anoxic zones, but mixers are placed within these zones to ensure that the bacteria maintain a uniform flock within the zone. And then finally, anaerobic conditions refer to conditions where there is no oxygen present, whether it be bound in a molecule or free. These zones are usually placed at the front of a treatment train to ensure that no oxygen is present there. And no aeration is added, but mixers are placed in these zones to ensure a uniform suspended flock of bacteria. Biological nitrogen removal is a two-step process within wastewater. The first step is called nitrification. Nitrification is where ammonia, NH4, is converted into nitrate, NO3. And nitrification occurs under aerobic conditions where free oxygen is present. The second step of nitrogen removal is called denitrification, which is where nitrate, NO3, is converted into nitrogen gas, N2, which then vents off into the atmosphere. Denitrification is completed under anoxic conditions, where no free oxygen is added, and the only oxygen present is oxygen that's present within the nitrate molecules. So this is an example layout of an MLE configuration, or modified Ludzak-Ettinger configuration. So as opposed to a normal aeration basin where we have one tank that is aerated, this configuration adds a pre-anoxic zone to the front of our treatment train. So we have a pre-anoxic zone and then an aerobic zone. The pre-anoxic zone is used to promote denitrification, so the conversion of nitrate to N2 gas. These zones are typically added at the front of a treatment train, and a mixed liquor recycle line takes bacteria from the aerobic zone and recycles it to the anoxic zone to supply it with the nitrate that it needs. Denitrification requires the correct amount of nutrients in the water to work effectively. So denitrification requires a ratio of 3:1 BOD to nitrate. And oftentimes, plants will have to dose carbon, often in the form of methanol, to get that right ratio of BOD to nitrate to perform denitrification in this zone. Oftentimes, optical nitrate sensors are used in these anoxic zones to measure nitrate and control the dosing of carbon in these areas. So this is an application example of an optical nitrate sensor, which was used to control carbon dosing in an anoxic zone at a plant. There was a side-by-side trial of 3 manufacturers' UV nitrate sensors. And in the end, YSI IQ SensorNet was selected due to the ease of installation, ease of use, and ease of maintenance. Particularly, they liked our modules, which can be stack mounted up to 3 modules per stack, which reduces the need for additional cabling between modules. Our UV nitrate sensor also comes equipped with ultrasonic cleaning, which will vibrate the probe periodically to remove buildup, which the operators preferred over the competitors' cleaning systems, which required maintenance. They also enjoyed our 2020 display, which is a portable display that can snap onto any module within a system to visualize sensor data at each measuring location. Additionally, our UV sensors have the ability to measure up to 5 parameters on a single sensor. So with our UV nitrate sensor, they chose to measure both nitrate and TSS on the sensor, which saved them an additional $4,000, which they would have sent on a separate total suspended solids probe. So this trial was very effective, and it led to UV nitrate sensors being installed in all 5 of their treatment trains to control carbon dosing, as well as 1 UV nitrate sensor in the effluent of the plant to ensure permit compliance. And then the final environment that we haven't talked about much is the anaerobic zone. Anaerobic zones are 0 oxygen environments, which are used to promote biological phosphorus removal. So phosphorus can be removed chemically or biologically from wastewater. We've talked about chemical phosphorus removal, which involves dosing chemicals. Biological phosphorus removal, on the other hand, is done through utilizing anaerobic zones. Anaerobic zones accumulate what are called PAOs, or phosphorus accumulating organisms. These PAOs are grown in the anaerobic zone, and then once they enter an aerobic zone downstream, they uptake all of the phosphorus out of the water. Anaerobic zones are zero oxygen environments, so they are typically at the front of a treatment train with a mixer there to keep bugs suspended. Oftentimes, ORP sensors are used in anaerobic and anoxic zones. ORP stands for oxidation reduction potential, and ORP sensors measure the net balance of all oxidation reduction reactions going on within the process. So all of the nutrients that are removed from wastewater, BOD, ammonia, nitrate, phosphorus, these are all oxidation reduction reactions which involve the transfer of electrons between molecules, and ORP sensors basically measure the net balance of free electrons within an environment. I kind of like to think of ORP sensors as negative DO sensors. DO sensors can tell you oxygen levels and thus can be used in aerobic zones, but they can't tell you anything about anoxic or anaerobic zones where we are not adding oxygen to the water. This is where ORP sensors are used typically in environments where DO sensors are not. These are typically used to verify that these zones truly are anoxic or anaerobic. So anoxic zones typically have an ORP value of negative 100 to plus 100 millivolts, so hovering right around the 0 mark. And anaerobic zones typically have a large negative ORP value of negative 300 to negative 100 millivolts. All right, I'll pass it back off to Justin.
All right, so we've got around 10 more slides left, and I will start the second stage off by talking a little bit about the secondary clarifiers, or also known as a final settling tank. So this is a part of the process in which we separate biological flock from the treated wastewater using gravity separation. The biological material from secondary treatment enters into the center of a clarifier, and then the organic solids sink to the bottom and are collected for distribution either to a return activated sludge system or to be wasted away in the wasted activated sludge. And then the clean water flows over the top of the clarifier and goes into a weir to either go into the effluent stages of processing and eventually tertiary treatment. So in this stage, having a sludge blanket level sensor can be really useful. Monitoring the sludge level height or even monitoring TSS can be used to help control the waste activated and the return activated sludge, which Adrienne talked a little bit about return activated sludge previously in this presentation. So sludge level sensors can be difficult to connect in these certain systems or in plants in general, which I'll talk about in a couple of slides, because typically we find that secondary clarifiers are farther away from the rest of the plant and where we typically see instrumentation. So in a couple of slides, I'll explain how IQ SensorNet can actually help mitigate the issue with running process instrumentation in remoter parts of the plant or more remote parts of the plant. But I would like to talk about this application example first. So this is an application example of an IFL demo that we have done in the past, where we were able to use our IFL sensors to actually get a customer to convert all of their online process instrumentation of the whole entire plant to IQ SensorNet process instrumentation. And it was based off the performance of this IFL sludge level sensor. So their original manufacturer for online analytical instrumentation that they used, they found that their sludge level sensor was not accurate enough to help control the processes that they needed to control. And really, really what they were trying to do was they were trying to maintain an optimum sludge blanket depth in their clarifiers to keep the correct amount of bugs in their aeration tanks and help support the secondary processes with that return activated sludge. So with the original manufacturer that they chose, they weren't able to keep that optimum sludge blanket depth or level because the sensors weren't accurate enough. So we did a trial with ours, and they found that ours were a lot more accurate, and they were seeing much better process efficiency when it comes to their return activated sludge processes, and then of course their secondary treatment processes by proxy. So those were the main benefits, and this application, like I said, they actually ended up utilizing 14 IFL sensors because this was a very large plant, as well as eventually switching over their complete suite of online sensors to the IQ SensorNet based off of this one sludge level probe. So it was a very cool application and a very nice success story on how our sensors were able to help improve the process of the plant. And then, like I said, a lot of secondary clarifiers in typical wastewater treatment plants layouts are a lot farther away from the rest of the process. So it can often be hard or taxing just to run cabling and wiring out to these remote locations in the plant. So what we have with IQ SensorNet is remote modules or wireless modules that use a radio frequency to communicate over distances of up to 100 meters. So as long as these two modules on the screen here have line of sight, it will communicate the sludge level height back to our controller, which might be sitting somewhere else in the plant, maybe on the activation basins or the aeration basins. So, or right outside of a control, right outside of a control house. So that is a unique benefit with our modular IQ SensorNet setup, is that we do have remote modules, and we actually do have a plant in Colorado that they opted to go complete remote sensor or remote modules. So they have no wiring connecting any of their measuring locations. It's all done through this wireless module. And that's how they run their plant, is completely off of these wireless modules. It's a pretty cool application. And I believe we have a webinar on that specific application with the operators on our website that's available to anyone who wants to learn a little bit more about that application. All right, so another secondary treatment control strategy is solids inventory control, or SRT, or what we want to control is SRT, which is solids retention time, which is the amount of bugs or the amount of time that the bugs actually spend in the secondary treatment basin. So these bugs need a certain amount of time in the basins to remove certain pollutants and to reproduce to maintain a healthy population. Carbon decomposition occurs within a few days, while nitrification takes a little bit longer. So common ranges for activated sludge or sludge retention time usually ranges around 3 to 15 days. So the way that we can control the SRT, the sludge retention time of any system, is with 2 TSS sensors and a flow meter. One TSS sensor is actually installed in the aeration basin to monitor the mixed liquor suspended solids, which is basically just a measurement of the amount of bugs. in the process. And then the other one is installed in a return activated sludge line, which is taking sludge from the bottom of that secondary clarifier that we just discussed and pushing it back into the secondary treatment basins. And so with that, with those two TSS sensors located, one in the aeration basin and the other one in the RAS line, and then a final piece of instrumentation, a flow meter in the waste activated sludge line, we can really fine tune and control exactly how many bugs we're sending back into the aeration basin to maintain a healthy mixed liquor suspended solids, and how much we're wasting away, how many of the bugs we're actually wasting away. And then, so this is an example of that application, actually, where we did a 2-month side-by-side trial with a couple other competitors. And we actually had to utilize an insertion mounting into the RAS line. So it might be hard to see, but up on that huge pipe, we've got one of our insertion mounts, our heaviest duty one, tapped into this return activated sludge line. And we had another TSS probe up in the aeration basin, measuring the mixed liquor suspended solids. And the plant operator said that if your sensor can work with our mixed liquor suspended solids, it will definitely work in the return activated sludge. And so we ended up doing a really good job when it comes to what they evaluated, which was they wanted to see how much short-term and long-term maintenance and how accurate the probe was over a long period of time. And so after the 2-month evaluation, they found that our sensors actually work the best. And as far as maintenance goes, our sensors, specifically the TSS sensors, work really well in these dirtier applications because we have ultrasonic cleaning on the tips of our total suspended solid sensors, which is basically ultrasonic vibrations that vibrate the sensor face and help keep the sensor face free from buildup of any sludge or any foreign materials that would otherwise affect the measurement. So and that is a completely non-mechanical way of cleaning. So there's no wear and tear parts when it comes to ultrasonic cleaning. And they really enjoyed that aspect of the sensor because it limited the amount of times they needed to pull the sensor out of the RAS line and clean it, as well as it helped enhance the accuracy of the probe over longer periods of time because that sensor face was staying cleaner for longer, allowing it to perform accurate and deliver reliable data. And the outcome of this application is, I believe, they ended up installing this, or going with our sensors and installing this strategy at 3 more facilities within their governance. All right, so finally we get to effluent treatment and monitoring. And so after secondary settling, water's typically very clear and it's almost ready to be headed out into the environment or sent to further tertiary treatment for reuse applications. But there still are some treatment and control strategies that go on in a typical wastewater treatment plant when it comes to disinfecting the water. And that is usually done via UV disinfection or chlorine dechlorination disinfection. And the goal of both of these processes are to remove any remaining pathogenic organisms that are left in the water. UV transmittance or UVT measurements or ORP and chlorine can be used to monitor the effectiveness of these processes. And we'll talk about each one of these. And then in addition to this, in general, for compliance monitoring, a lot of the permits are built around PHDO, ammonia, turbidity, BOD, and phosphates. So, and in some places, ammonium. So we like to monitor those, and those are important to monitor just to ensure that we are staying within the permit regulations and staying compliant with that. So let's talk about UV disinfection control. So this is an example of a typical layout where we've got a UVT 254 probe a little bit upstream from a UV disinfection channel. And what we're measuring here is UVT transmittance percentage. So the amount of UV light that can be transmitted from one side of the probe to the other side, where we detect that and determine the amount, the transmittance level. And so what this probe will do is when it ties into a UV disinfection system, it's going to give that UV system a heads up on how clean or dirty the water is based off of the UVT value. And that is going to let the UV channel and the UV lamps know exactly how much intensity of UV light needs to be utilized to treat the water passing by it. So it optimizes what this control strategy does is it ends up optimizing the amount of energy that is used to effectively clean the water. So if the UV transmittance is higher, that indicates that the water is cleaner. So the UV lamps don't have to dose as much and they don't have to utilize as much power. But if the UV transmittance on the probe is a lower percentage or a lower value, then the lamps know that to create peak or sufficient amount of dosing, they're going to have to turn up the intensity of the UV lamps, which may increase the amount of energy used, but you're ensuring that you're always at the minimum level for sufficient cleaning of the water. And then a system like this, just a UVT probe, as well as a controller, ends up being around $20,000, which the UV or the return on investment is typically short, like we see with the orthophosphate analyzers within a year, because of the amount of energy we end up saving on UVT lamps. And you can also include the lamp bulb replacements. If we're running the UV lamps at a highly efficient rate, the amount of time in which you need to change them out will increase. So there's a lot of added cost savings to implementing an online system with the UVT system. All right, and then another way that we disinfect water is with chlorination, dechlorination, which is a typical strategy that is used in wastewater treatment plants and also wastewater plants, or sorry, clean water plants. But for the purposes of this presentation, we'll just talk about chlorination, dechlorination as it relates to wastewater treatment. And so you can use two different types of sensors for this. You can use a chlorine analyzer, which we have a 3017M chlorine analyzer, where we'll typically place an analyzer at the beginning of the process, sometimes in the middle of the process, and then finally at the end of the process. And basically the way that a chlorination dechlorination system works is that we're going to dose, in most cases, sodium hypochlorite at the beginning, and then let the water flow through these contact basins. And then once we meet a desired residual, we'll start the dechlorination process, which is typically done by dosing, I believe it's sodium bisulfate, to remove chlorine before we discharge it, because there's typically a 0 or close to 0 discharge limit or chlorine in when it's going back into the environment. So we can either do this by adding a few analyzers into these contact basins and right at the effluent, and we can do just depending, you could do a feedback or a feed forwards system where you're either checking the dosage at the middle of the contact basins and feeding back to the chemical doser and letting the doser know if it needs to dose more or less based off of a desired residual. Or you could do a feed forward where you are measuring different parameters in the water and then right before dosing and seeing, I guess, the amount of residual that would be chlorine residual that would be needed to effectively chlorinate the water. And then at the very end of the process, you would want to have a chlorine analyzer to ensure that the sodium bisulfate has dechlorinated down to the permit limit. This can also be done with ORP measurements if a chlorine analyzer is not applicable or is not in the budget per se. ORP values correlate, the millivolt values can correlate to the amount of chlorine in a system, but all the processes are very similar. And then finally, we will talk about effluent monitoring. So this is an example of a system where a wastewater plant is measuring DO and pH as well as turbidity for compliance assurance. These 3 probes were installed into a flow-through mounting set, and they were set to alarm and alert the operators as soon as any of those parameters went outside of the permitted range. And this is strictly for just compliance assurance and monitoring and allowing operators to react more quickly when any sort of upset or permit requirements are broken at the effluent. And then I believe we've got one more slide just to quickly touch on tertiary treatment and sludge level treatment. So these are some additional treatment stages where instrumentation can be used in tertiary treatment, which is usually an additional stage of clarifying water that's going to be used in a reuse application. It requires a lot of monitoring to achieve a high quality water product that can be used for reuse applications. So we typically see DO, pH, orthophosphate, TOC, and turbidity monitored here, and they are all used in some way, shape, or form for compliance monitoring and process control. And then also for the sludge treatment side of the wastewater plant and removal of sludge, we can monitor pH, TSS, DO, and ORP for early warning signs, and then also to help make the process a little more efficient. And with that, we'll wrap up the presentation. If you have any questions about how online instrumentation can improve wastewater treatment plant processes or help with compliance assurance, feel free to reach out to myself or Adrienne directly. And then also online at ysi.com, we have a lot of case studies and solutions, documentation, as well as tons of other webinars and great educational content kind of centered around wastewater treatment processes and online instrumentation. So feel free to browse on our website if you're curious about any other case studies or applications.
Right, thank you, Justin and Adrienne for This is a rather comprehensive presentation this afternoon. I think we had quite a number of people online, so it's now open for them if they should have any questions. Please proceed. I haven't seen any in the chat just yet, but I think there are quite a few of you who are water operators and plant operators. So feel free to pose your questions at this stage. Of course, I think some of what you presented in the early stages were on the online systems that you have. And for making the orthophosphate analyzers, which you said would make busy operators would find more time to do other things on the plants because of the systems that you have. And I also observed that you mentioned about your process control systems, the secondary system treatment with the anaerobic, anoxic, and aerobic processes. I'm sure somebody must have some questions here as operators. But if there are none, then I'm sure the contact information is around. Oh, Kevin has a question. Please go ahead, Kevin.
Hi. Well, first of all, I just want to thank them both. Like you said, Ignatius, just an exceptional, comprehensive and walkthrough through a wastewater facility and how your instruments help optimize, managing water quality requirements. A couple of things, I guess. One, could you talk about, how the instruments, how much time is in the training of using them, and also, some of the things that go into the calibration and that type of stuff. And then we've had a lot of nature-based wastewater treatment presentations in this forum, and I'm sure you have some of those that YSI has worked on as well. Working to understand the water quality through those types of systems.
Yeah, so as far as maintenance and training goes for our IQ SensorNet system, typically when we're setting up a new system, we offer some sort of training services, and we actually have a lot of online materials that cover kind of the different calibrations that are needed to keep these sensors giving you reliable and accurate data. In general, we try to make our instrumentation as maintenance free or as maintenance light as possible. So for example, our FDO, our dissolved oxygen sensor, it has been manufactured and designed in a way where it not need to be, it's factory calibrated and it does not need to be regularly calibrated throughout the lifetime of the sensor. That's because we use a smart DO sensor cap that has the factory calibration stored on it. And then we use the same measurement technology when it comes to our measurement pathway and our reference pathway within the optical DO probe. So that one is a fan favorite amongst operators because they don't have to regularly calibrate that instrumentation, and it saves them a bunch of money when it comes to DO and lower cost running those. Other probes like the RTSS and turbidity probes also come factory calibrated and may need to be adjusted depending on the process over the time, but are fairly maintenance light as well, as long as they have the ultrasonic cleaning feature turned on and are pulled at a somewhat semi-regular basis to be cleaned. Those are very maintenance light. And I should mention that all of our sensors that do need to be calibrated or have some sort of matrix adjustment applied to them the controller actually walks you through a step-by-step process on how to do that. So it's very nice. We've tried to make it intuitive and add wizards to kind of walk the operators through that, as well as our tech support is available Monday through Friday, 8 a.m. to 5 p.m. for phone calls and questions about those sorts of things.
Great. Thank you very much. Again, this is recorded, so it's a great walkthrough of the systems themselves and your probes. And then just real quick, nature-based wastewater solutions, like in wetlands and those types of things, it's very applicable as well, correct?
Yeah, I would say probably, if I'm understanding correctly, that are you talking about measuring in wetlands and environmental spaces?
Yes, right.
So we have a suite of sensors or probes that are called the EXO series, and they're for environmental monitoring, and they're meant for so where they differ from the IQ SensorNet product line is IQ SensorNet is meant for 24/7 monitoring and deployment. The EXO series for measuring out in the field where you might not have reliable access to power. They're meant for semi-permanent deployments, and I believe some of those probes can be deployed for up to and over 6 months at a time, collecting data and sending that data back. But that would be all covered under the EXO series. And admittedly, I know we do a great job with those probes. I just don't know too much about them because they aren't under my purview.
Gotcha. Okay. Thanks again to you both.
Yep. Thank
Okay,
you.
we have a question in the chat. Thank you again for this question, Kevin. For nature-based treatment, there seems to be a lot of fouling of the sensors. Does repeated cleaning shorten the lifespan of the probes?
So I would say for the IQ SensorNet probes, repeated cleaning will not shorten the lifetime of the probe as long as it's not excessive and aggressive cleaning. So for example, for the ion selective electrodes that we were talking about, the ammonium and nitrate sensors, they use electrode-based technology to determine ammonium nitrate, phosphorus, or chloride and potassium, not phosphorus. And we've made these electrodes with a stainless steel mesh over the face of the electrode so that they can withstand and endure rugged environments. So you can clean those fairly aggressively and that won't shorten the lifetime of the electrode. But with anything, if you take it to an extreme or excessive manner, it could, for example, the dissolved oxygen probes are, they have a laminated sensor cap. And if you excessively clean that, you can delaminate that sensor cap. And although it won't ruin the entire probe, it will cause you to replace the consumable part of the probe, which is the dissolved oxygen cap, more frequently. I should mention too that we do offer a variety of different air cleaning application or options as well. We've got 3 different air blast cleaning systems where we actually take compressed air and blow it over the sensor face at different time intervals. And we've got kind of like a medium, a high level, and a low level PSI cleaning options that allow us to clean the sensors while they're in situ, while they're in the process. And that helps elongate the lifetime of the sensor, as well as it helps elongate the period of time in which an operator would need to pull and do any sort of manual maintenance on the sensor. For the nature-based treatment, so that would be the EXO series sensors. I know a lot of the EXO series sensors are based very similarly off of what we talked about today, which is IQ SensorNet. I know that I'm not sure if they use air cleaning for EXO, but I do know they utilize some sort of mechanical wipers to keep those sensors clean out in the field for longer periods of time. Often those sensors are deployed in remote locations where regular cleaning isn't an option, just because the people deploying them can't get out into the field that often. So I know that they have came across this before and have solutions for it. Specifically, other than mechanical cleaning, I'm not quite sure though. Hopefully that helped answer the question.
Okay, thank you for that, Justin. Are there any other questions? No other questions in the chat thus far.
Hi, good afternoon.
Oh, good afternoon, Alison Elcock. Please
Hi,
proceed.
Alison Elcock, Trinidad, from WASA and also the Wastewater Specialist Group of CWWA. Thank you so much for this presentation. Very, very interesting indeed. I wanted to find out if we're interested in acquiring any of these sensors. Do you also offer services of assessment, or would we need to know where we have to place the probes? I know that you said that there were trials and they would have tried different spots along the treatment process, and so they found out how they could optimize the use of the probe. Would you, with your experience, be able to come in and do an assessment for us if we, wanted to get these probes installed? Would you be able to give that sort of advice as well?
Yes, definitely. So we could do that in a variety of different ways, either through our reps who are very knowledgeable, can come into the physical plant and kind of explain where and what are the best places to deploy certain sensors to give you the most value out of a process instrumentation network. Specifically, if you're not working with much budget, we can give you the most value for the least amount of money, which is typically in most plants going to be aeration control. But then also virtually, we can definitely meet and talk about the needs and wants of the plant. We're actually on our website. Let me go to that and show you. We have a program where you can do a free consultation for with one of us, Adrienne or myself, for an hour. And if you just fill out the form, and we can actually talk about the different applications you'd like to deploy sensors in. So right here it says consult municipal experts on our homepage. And if you click on that, it'll take you to a sign up form, and then we'll get an automated email where we can talk specifically about your plant's applications and any opportunities that you might want to look into when it comes to deploying online instrumentation. On top of that, if you're not quite sure and you don't want to buy a full out system, we do offer demos. So for that, we'd want to get you involved with the local reps and the regional sales manager, which is on this call, Yusuf. And they could possibly provide some sort of demo equipment to try to do as kind of like a trial to test and see if our instrumentation would be beneficial at your guys' plant.
Sounds great. Thank you so much.
Yep, and I will put this link in the chat in case anybody's interested in it.
Thank you, Alison. Do we have any other questions? Okay. I think we have had you for the better part of 90 minutes. And we would like to thank you immensely, Justin and Adrienne of Xylem, for sharing this time with us and sharing your expertise. And if it's Wednesday, CAWASA always tries to find our operators, the experts on various subjects from A to Z in the water and wastewater sector. And we look forward to seeing you again next week, Wednesday, same time, 4 p.m. And we will send you the link later this week to invite you to our next webinar. So we thank you very much for joining us on this webinar number 11, and wish you a very good evening. And thank us also especially to Fishala Maharaj, who made the connections and got you on board with us today. Excellent presentation. And of course, it's been recorded. We will certainly be sharing it with all the participants. And you may also check out our YouTube, CAWASA Education at YouTube. And please share and like. Thank you very much. And subscribe. Thank you very much. Have a good evening.
Thank you.
Bye, everyone.
Thanks again. Bye.
Bye.